Okay, today we're going to look at what's called infinite series. A series is when you take an infinite sequence and you add the terms. So I'm taking a of 1 plus a of 2 plus a of 3 all the way forever until I get to n is infinity. And this is called an infinite series. So adding sequences makes a series. Now to find the sum of an infinite series, consider the following sequence of partial sums. So we first find we find the partial sums and we kind of look at a pattern. So how do you find the partial sums? Well, you just add up those many terms. So if I want to find the partial sum s of 2, that means I'm going to add the first two terms of this series. So the first two terms of this sequence is 1/2 and plus 1/4. So the series would be 1/2 plus 1/4, which is 3/4. That's the partial sum for this one. So find our s of 3. So I have the 1/2 plus the 1/4. Now I'm going to add a 1/8, which will give me 7/8. Now to find an infinite series is an expression of the form s is equal to the summation as n equals 1 to infinity of a sub n. How we find this is we're going to take the limit as n goes to infinity of our s of n, our partial sums. So limit as n goes to infinity of our s of n partial sum. Okay, that is the infinite series is the limit of the nth partial sum. If the infinite series approaches a value s, it is said to converge to a sum of s. If s does not exist, the infinite series is said to diverge. So let's determine if this series converges or diverges. If it converges, we'll find the sum of the series. So let's look at our first few partial sums. So our s of 1 sum is equal to 1. Our s of 2 sum is 1 minus 1, which is 0. Our s of 3 sum is 1 minus 1 plus 1, which is 1. S of 4 sum is 1 minus 1 plus 1 minus 1, which is 0. So hopefully you can kind of start seeing a pattern here. If you need to do another s term, go ahead until you see a pattern. But notice our sums are alternating between 1 and 0. So anytime it alternates, we know our series diverges. So we can say this series diverges because this series has no sum, or our partial sums are alternating. That's a kind of way to look at this one. Okay, we're going to do the same thing. We're going to determine whether a series converges or diverges. If it converges, we're going to find the sum. But I'm going to show you another way of doing it. This is a more common method of doing it than what we just did in this example 1. Okay, so we have this series k equals 1 to infinity of 1 over k times k plus 1. Okay, so one way to do this is I'm going to look at that fraction, that rational term there, and I'm going to do partial fraction decomposition. So I'm going to rewrite 1 over k plus 1 as a partial fraction, as like a over k plus b over k plus 1. So remember, our partial fraction, we got a common denominator, so I got that 1 on the right-hand side is equal to a times k plus 1 plus bk. And so I got a root of 0, so I'm going to let k equal, well, -1. I have a root of -1 as well. And so plug in that -1, I see b is 1, or -1. And then I'll let k equal 0, and I'll see that a has to equal 1. So I can rewrite this series as the summation of k equals 1 to infinity of 1 over k plus a -1 over k plus 1. So let's look at the s of n, the nth partial sum for this series. So I'm going to kind of expand this out. So the first one would be 1 over 1 minus 1 over 2. If I'm plugging into that bottom fraction, the partial fraction decomp I just came up with. My second s of 2 would be 1/2 minus 1/3. My s of 3 would be 1/3 minus 1/4. And this would go on. And my s of n, n minus 1 term would be 1 minus n minus 1 minus 1 over n. And here's my n plus 1 term. Now notice, cool thing happens. All of these middle things cancel out. And all I'm left with is my two outside values, 1 minus 1 over n minus 1. So that's actually what my nth sum would be for this series. Isn't that cool? Okay, so let's see if we can get a limit as n goes to infinity of this s of n. Well, that would be the same as limit as n goes to infinity of 1, which is 1, and the limit is minus the limit as n goes to infinity of 1 over n plus 1, which is 0. So that limit goes to 0, so I know this series converges to a sum of 1. Now we're going to learn a special type of series called a geometric series. And geometric series is in the form s is equal to the summation of n minus 1 to infinity of a times r to the n minus 1, which is if I wrote out that series, that'd be a plus a times r plus a times r squared plus a times r cubed, etc., all to a times r to the n minus 1 power would be our nth term. Okay, key is a cannot equal to 0, and that r I wrote in that formula there stands for the common ratio for the series. Okay, let's look at how we can do this. So we're going to notice our pattern for this first one. Our first term is 2 to the 0, 2 to the 1, plus 2 to the square, plus 2 cubed, etc. So I notice my a sub n term here. If n equals 1, I notice I have my formula for a sub n would be equal to 2 raised to the n minus 1 power. So rewriting that, I have my a is equal to 1. This is in that form that we set up. And my r is simply the 2 value. Okay, I want to repeat that. Let's look at the pattern here. I got 3 over 10 plus 3 over 10 squared for our second term, plus 3 over 10 cubed for our third term. And so my a sub n term for this would be 3 over 10 cubed, or 10 to the nth power. But that doesn't fit our form. So I'm going to factor out a 3 to the 10th. And then when I factor out 3 over 10, that leaves me 1 over 10 to the n minus 1 power. And then I can take that, since 1 can be raised to any power and still be 1, I'm going to rewrite this as 1 over 10 to the n minus 1 power. So sometimes you'll have to rewrite it a little bit to make it look like your a sub n term look like the geometric series format. And so now it looks like that geometric series format. I can say that my a term is equal to 3/10 and my r term is 1 over 10. Okay, you try C. Okay, so first I'm going to write out the first few terms to see if I can figure out the pattern. So I notice that my signs are alternating and my numerator stays 1. My denominator is just a power of 2. And notice the power equals my number of terms. So I can rewrite this as 1 over 2 to the n. Well, if I do that, I don't get the alternating. Okay, so I need to figure out how to get a positive for my first term, a negative for the second term. So I'm going to multiply this by -1, but I need to figure out, should that be raised to the n power or the n plus 1 power? And so to figure that out, I need a positive for the first one, so it must be raised to n plus 1 power. So our a sub n term is -1 to the n plus 1 times by 1 over 2 to the n. Okay, so I need to rewrite this in my summation kind of formula for a geometric series. And so let's disregard the alternating part right now, that -1, and let's see if we can figure out the other part. So I need to factor out my one of those 1 over n so I can get an n minus 1 power. Okay, so let's check our first few terms, see if we can get those terms we listed over there. So if I let this go to the n minus 1 power, so if I plug in n is equal to 1, I get 0. Well, that's 1/2, so that works. For n equals 2, 2 minus 1 is 1. So 1/2 times 1/2 does give us 1/4. Yes. So this is working out pretty good. The only problem is I'm not alternating signs. So let's try making the r negative and see if that works. And as I work through it, I figure out that, yeah, that gives me my signs change because I'm going to raise even and odd power. So that's going to be my geometric series. And so now I need to figure out what my A term is, which is 1/2, and my R term, which is negative 1/2. Now we know how to identify and write a geometric series. Let's look at what's called a geometric series theorem, which lets us tell when a geometric series converges or diverges. The basic rule is if the absolute value of r is less than 1, the series will converge. If the absolute value of r is greater than 1, the series diverges. That's simple. And if it converges, the convergence of any geometric series in the form of a times r to the n minus 1 is simply a divided by 1 minus r, always. Okay, so let's look at our A, B, and C example from above, and we're going to figure out these two series converges or diverges. So in our first one, we had A is equal to 1, R is equal to 2. So the absolute value of 2 is greater than 1. So by our geometric series theorem, this diverges. Okay, looking at B, we found that A was equal to 3/10 and R was equal to 1/10. So the absolute value of 1/10 is 1/10. 1/10 is less than 1. So this series converges. Now we're going to find the sum that it converges to. In the series it converges, I just take my A, which is 3/10, and divide it by 1 minus 1/10, which will give us, 3/10 over 9/10. Flip and multiply the bottom fraction. That'll give us 3/9, which therefore simplifies down to 1/3. So this series converges to 1/3. Okay, looking at the C, the last one, we had our A is equal to 1/2, our R was equal to negative 1/2. The absolute value of negative 1/2 is 1/2. 1/2 is less than 1, so yes, it converges. And our sum, again, we take our A divided by 1 minus R. So that's going to be 1/2 over 1 plus 1/2, which is 3/2. And 1/2 divided by 3/2 gives us 1/3. We can also use geometric series to rewrite repeating fractions as decimals without the use of a calculator. So first you notice how many terms repeat. So notice there's 3 terms that repeat. So that's 0.001 of repeating. And so what you do is you take the point that you have, the repeating decimal, which is 0.784, and you times it by 0.001, because there was 3 digits that were repeating, to the n minus 1 power, to rewrite this as a geometric series. And you can test yourself. Plug in n equals 1 and see if you get what you get, and then add that to n, when you n plus 2, adding that to n plus 3, and you're just going to keep getting one more repeating each time. And so here we have a geometric series where A is equal to 0.784, R is equal to 0.001. So we can find our sum of that because R is less than 1, so it converges by using our formula A over 1 minus R. And we get 0.74 over 0.999. So multiplying each of those by 1,000 to get rid of the decimal, we get 784 over 999. And that is the decimal equivalent of this repeating fraction. Repeating decimal. This is the fraction equivalent of our repeating decimal.